All right, so we're going to go ahead and talk through how to do this. I'm going to show you one way to do it, and then I'm going to do it a slightly different way to get you the same answer, just to show you guys that there are a variety of ways to do this and do this correctly. What's really going to be important is that you understand why you're doing all the steps, and you're showing your work, so that if anything ever goes wrong, you can earn some partial credit. So looking at part A, what I was kind of saying as I was walking around is that I like to approach all of my dilution problems in the same way, which is I think about what's actually happening. Okay, so to me, a dilution problem is a lot like making orange juice from that frozen concentrate, if you've ever done that, is that you take the frozen concentrate, you put it in the container, and all you add to it is water, right? There's no possible way for any more orange stuff to get in there. So that orange stuff we can think of as the moles. So once we put in the moles of our concentrated solution, that's never going to change. There's the same number of moles in the concentrated solution as there are in the diluted solution. So the moles are always staying the same. The only thing that we change is the amount of volume that those moles are dissolved in. So that's where the adding water comes in. The biggest point people kind of get confused on these types of problems is they get really used to using a formula like M1V1 equals M2V2, and then they start applying that formula to situations where it doesn't actually work. So please make sure you're actually doing a dilution, and the way you can tell you're doing a dilution is that it's the exact same substance before and after. So you can see in this case, we're starting with 6 molar HNO3, and we're ending with 0.5 molar HNO3. We haven't done any chemical reaction, there's no new substance, we are just adding water to it and decreasing its concentration. So that's how you can tell that it's a dilution problem. So like I said, the first thing I like to figure out is how many moles I'm starting with, or how many moles need to be in my container. So they're asking us how many milliliters of the stock solution, and the stock solution is just another way to say concentrated solution. So normally when we order chemicals, we like to order them concentrated, and we dilute them once they get here, because if we paid for people to ship us water, it would get very expensive. So it's called a stock solution because it's concentrated, and that's what we keep in the stock room. So we've got our stock solution here, and I need to make 110 milliliters of a 0.5 molar HNO3 solution. So what that is telling me is how many moles I need to have at the end of this, because it's giving me a molarity and a volume, and with a molarity and a volume, I can figure out moles. So that's the first thing that I'm going to do, is I'm going to say that I know this is 0.500 moles per liter, because that's just another way to write out capital M. And I know that I'm going to use 0.110 liters of that, so converting my milliliters into liters. And what that tells me is that I need 0.055 moles of HNO3. Now I haven't quite answered the question yet, because the question asked me how many milliliters of that stock solution I need. So essentially what I'm saying now is that that concentrated 6 molar solution, I'm trying to figure out what volume of that solution contains 0.055 moles. Does that explanation make sense? Is it going to take me a full 110 milliliters of that concentrated solution? No, it should take me much less of the concentrated solution, because that's what I'm going to be diluting. So what I like to do here is think of the 6 molar as almost a conversion factor and say, okay, I want 0.055 moles of HNO3. I know that I have to get that from my stock solution, and that in every 1 liter of my stock solution, there are 6.0 moles of HNO3. So it's still the molarity. I'm just turning the units upside down so that I can use it to cancel out moles. And when you do this, you're going to end up with a very, very small number, 0.0092 liters. So the last thing I want to do is answer that the way the problem asked me to, which is milliliters. So you should have 9.2 milliliters. So you would pour out 9.2 milliliters of the stock solution, and then you would add enough water to reach 110 milliliters. So you're only going to add about 100 milliliters of water. Any questions on the logic in that one? Okay, so let's take a look at part B. So part B is related to part A. So we're taking the same stock solution. So it's still a 6 molar stock solution, and now I'm going to dilute it to a final volume of 0.250 liters, and I want to know what the concentration of that diluted solution is going to be. Would you expect that new concentration to be larger or smaller than 6 molar? what happens to a concentration when you dilute something? It becomes less concentrated, and numerically that's going to translate to being a smaller number. So it's always good just to make sure your answers seem reasonable. So I'm going to show you how to do this one using the M1V1 equals M2V2 equation. It's going to be the exact same way you would do it no matter what. It's just a little faster if you understand the equation. Okay, so the capital M's in this case stand for molarity, just like they always have. Capital V's stand for volume. 1 and 2 you can think of as standing for before and after, or concentrated and dilute, or stock and dilute, or whatever you want to do. But just realize that the ones go together. It's the molarity and volume of one solution, and then the molarity and the volume of the second solution. So make sure you're matching those up appropriately. So if I decide that I want my stock solution to be solution 1, I already know the molarity of the stock solution is what? Yep. Okay. And do I know the volume of stock solution that I'm using? Yeah, they told me it's 10 milliliters. Okay. Do I know the concentration of the diluted solution? No, that's what they're asking me, right? They're asking me what is the concentration going to be? Do I know what the volume of the diluted solution is going to be? Yeah, what is it? Yep. Okay, and it doesn't matter if you do these both in milliliters or both in liters, it just matters that the volume units match. So whichever one you prefer, just make sure that they match. So all you need to do at this point is solve for M2, and you should get 0.24 molar. So that would be your concentration of the diluted solution. Yeah.
When I did it, I didn't change the 10 milliliters to liters, and I still got the same answer.
You didn't change it to liters. If you did 1 in milliliters and 1 in liters, your math shouldn't have worked out. Did you convert the 250 liter? Is that what you did? As long as they're both the same unit, it's fine. So if you did them both in milliliters, that is totally acceptable. They just have to be the same unit or they won't cancel.
Okay.
Yeah, so liters is fine, milliliters is fine, they just have to match. That's the important part about the units. Any other questions about this one? Okay, so again, a few more points just to make really clear. This equation, M1V1 equals M2V2, only works if this is a dilution. And I can tell it's a dilution because it's the same chemical before and after. So this is not a stoichiometry equation. You can't just do this anytime you see molarities. Now, it only works for dilutions, so make sure you're definitely doing a dilution problem. If you're not sure, you can never go wrong just doing the moles thing. So the way I showed you in part A, that will always work, even if it happened to be a stoichiometry problem, because you're still thinking about mole ratios and things like that. So M1V1 equals M2V2 is a nice shortcut, but don't use it unless you're entirely sure that it applies in that situation. Any other questions about this before we move on to something a little harder? All right. All right, so writing out this balanced reaction, I know I've got KOH. Since they told me I've got a solution, that means it's aqueous, and I know I'm mixing that with NiSO4. Again, I know it's aqueous because they told me that I've got a solution there. So I need to think about how these things are going to switch partners. The potassium is now going to be paired with the sulfates, and we just need to make sure we're checking the charges. So since the charge on potassium is +1, but the charge on the sulfate is -2, that means I'm going to need 2 potassiums for every sulfate. So make sure you are checking the charges. You're not just recombining things in a 1-to-1 ratio. Any questions about why that formula is K2SO4? Okay, so if I go back and write all the charges on top, K has a +1 charge, hydroxide has a -1, nickel has a +2 charge, and sulfate has a -2 charge. So when I repair the K with the SO4, I can see that their charges won't work unless there are 2 potassiums. So similar idea when I combine the nickel with the hydroxide. Since nickel has a +2 charge, it's not going to work with only 1 hydroxide. So you just use parentheses to indicate that you're going to have 2 hydroxides there. Okay? So notice that I haven't put in states yet. I'll get to that in a second, but we can go ahead and balance it at this point. So you should have used one coefficient, and that should be the number 2 in front of the KOH. So that's all you needed to do to balance this reaction. Questions up to this point? Okay, so let's talk about which one is the precipitate. So if you look at your solubility rules, SO4 sulfates are usually soluble. One big exception for that is if we've got barium, but we don't. Hydroxides are usually insoluble. A big exception for that is if we have the alkali metals, so sodium, potassium, things like that, or some of the alkaline earth metals. Since nickel is not one of those, and we know that hydroxides are usually insoluble, makes sense that this is going to be our precipitate, the nickel hydroxide, which means that I should give what state to the K2SO4? Yep, it's going to be aqueous. All right, so that takes us through the first 2 parts of this. Next thing we need to think about is which one is the limiting reactant. In order to figure out which one's the limiting reactant, I need to know how many moles of both of them I start with. So we always want to do comparisons in moles because the balanced chemical reaction tells us mole ratios. So we practiced this when we did the dilution problem, but since I've got a volume and a concentration, right, a V and an M, I can get moles. So that's all I'm going to do for these 2. Okay, so if I just multiply the concentrations by the volumes, and notice that I've changed my volumes into liters because concentration is in units of moles per liter, so I'm multiplying it in liters. So I see that I started with 0.02 moles of KOH, and I started with 0.03 moles of NiSO4. So I can already see that I started with more of the nickel sulfates, but which one do I consume faster, according to the balanced reaction? Yeah, I go through the KOH faster, and how can you tell that I'm going through the KOH faster? Yeah, that's exactly what the balanced reaction tells me. It says I'm going to use 2 moles of KOH for every 1 mole of NiSO4. So if I'm going through it twice as fast, and I start with less of it, that is definitely my limiting reactants. Okay? The other way you can think about it is you can divide the moles by the coefficient, so 0.02 by 2 and 0.03 by 1, and you can see that you're going to have a smaller number for the KOH, and that again confirms that it's your limiting reactants. So now that you have that piece of information, you should be able to move forward. I'm going to go ahead and show you what this looks like in an ice table, just because this is how I do my problems. But you'll see that it matches all of the work you normally do for these stoichiometry problems. So I stands for initial. We said we started with 0.02 moles of the KOH, 0.03 moles of the NiSO4. How many moles of product do we start with? No, there's no product because we haven't done the reaction yet. Okay. We can think of the C row as standing for change or coefficients. This is essentially telling me what my moles are going to change by. So you already told me that the KOH is going to change by a factor of 2, but the NiSO4 is only going to change by a factor of 1. And since those are reactants, we are going to be consuming them. To indicate that we're consuming them, I'm going to give it a negative sign. So I'm going to say -2 whatever, -1 whatever. And the reason I'm saying X is because I don't know exactly how many times I'm going to run this reaction. I don't know if I'm going to run it a whole time or 10 times or half of a time or a third of a time, but I know that whenever I run it, there's a 2-to-1 factor in how fast I go through the KOH and how fast I go through the NiSO4. Any questions on what those numbers are standing for right there? If I do the same thing on the product side, I'm going to say plus 1x for both of these. Why would I put a positive sign for the products? Yeah, because every time I do a reaction, I should be making product. I should be increasing the amount of product. And why would the number 1 be in front of both of those? Yeah, it's the coefficient. They increase by a factor of 1. So that's all the C is for. All right, and I'm just going to show you that the limiting reactants work the same way. Yeah.
So the reactants are always going to be negative.
Yeah, exactly. Because every time I run a reaction, I get rid of reactants, but I increase products. So it'll always look like that. All right. So we're going to do mathematically what we just kind of did out loud, which is I'm trying to figure out which one I'm going to run out of first, this one or that one. So if I run out of it, that's essentially like saying how much I have at the end is 0. So one option is that at the end I have 0 KOH, and 0 is equal to 0.02 moles minus 2x. And the way I'm doing that is I'm just reading right down the column. I'm saying I started with 0.02 moles, they're changing by a factor of 2x, and if I run out of it, at the end I'll have 0. So that's where this setup came from. If I solve that, x 0.01, just like you would normally do if you divided your starting amount by your coefficient. Okay, what if I ran out of the nickel? Same idea. If I ran out of it, I'd have 0, and that would look like 0.03 moles minus 1x, so x would be equal to 0.03. So anytime we talk about a limiting reactant, what number do we keep? Do we keep the big number or do we keep the small number? We always keep the small number because that's what's limiting. So we'd say, all right, this didn't happen. That was just for comparison. This is what's actually happening. X is going to be equal to 0.01, which means I'm definitely going to have no moles of that at the end. What's 0.03 minus 0.01? Any questions on why I'd have 0.02 moles of NiSO4 left over at the end? Okay. So if I called KOH my limiting reactant, what would be a good name for NiSO4? It would be my excess reactant. And excess means that there has to be some of it left over at the end. If I want to think about this algebraically, I'm going to go ahead and do it down here. I can say that I started with 0.03 moles. It decreased by a factor of 1 times 0.01 moles. So 0.03 minus 0.01. That's where the 0.02 came from. I'm just literally plugging in the 0.01 moles for x. I'm trying to show you how much it decreased by. Still questions on that? I can try to explain it again. Yeah.
So you just take whatever the limiting reactant was and subtract that from that reactant?
As long as you're essentially plugging in x. So the reason I could subtract it is because it's 1x here, but if it had been like 4x, I would have just needed to make sure to multiply by a factor of 4.
Okay.
So I need to make sure that the coefficient is part of that. I know this looks weird, but so questions, I'm more than happy to explain how this works. Okay, applying the same idea, if I know that this is increasing by 0.01, that tells me how much product I have at the end. So how many moles of each of the products should I have? 0 plus 1x. So again, I'm using the same value of x we found because it's limiting reactant. I'm reading down the column and I'm just plugging in the numbers. Again, using the coefficient of 1, if it had been 5, it would have been 5, but just using the coefficients there, and that's why I figured out how many moles of product I have. This will match any work you do using the normal cross stoichiometry. It's just a visual way to represent it so you can see it all in one table. So any questions on where any of those numbers are coming from?
Not numbers, but what does ICE stand for?
I for initial. C, I can either call change or coefficients, whatever you like better for C.
And then E is
E for end, yeah. Other questions? Okay, So at this point, you should have enough information to do part D and part E. All right, so what we're trying to do now is we're trying to figure out how many grams of the precipitate formed. So if you think back to the ice table or the numbers that we had written down, you should know how many moles of the precipitate formed. So how many moles of the precipitate did we have? Yeah. And we know that the formula for precipitate was NiOH2. So if I know the moles, how do I get that back into grams? Yeah, I need the molar mass. So if you have your periodic tables here, hopefully you added up 1 nickel, 2 oxygens, and 2 hydrogens, and you should have gotten something around 92.708 grams. And doing the math, 0.927 grams of that nickel hydroxide. So that one should have been pretty straightforward, because as soon as you know how many moles of the product you have, you just need the molar mass to get it to grams. Any questions about where any of those numbers came from? So the 0.1 for me came from the previous slide. What they're asking us to do now is try to figure out the concentration of everything that's left in solution. In order to figure out the concentration of everything that's left in solution, the first thing I want to know is how much solution I have. So what is the total volume of my solution that I need to work with? So you should have written down from the problem that we started with 100 milliliters of the KOH and 200 milliliters of the NiSO4. So what's my total volume now? Perfect. All right, so we're going to need that piece of information a little bit later. The next thing we need to think about is how much stuff did we have after the reaction was complete? So essentially what I'm going to do is I'm just going to replicate the bottom row, that end row, because that tells me what I have after the reaction was complete. After this reaction was complete, I had 0 moles of KOH. I had 0.02 moles of the NiSO4. I had 0.01 moles of the K2SO4. And I had 0.01 moles of the NiOH2. All right, so the question is, what all do I have left in solution? Okay, I can't have any KOH in solution because I used it all. Are we comfortable with that idea? I don't have to worry about that. There's another one of those up there that I don't have to worry about because it's not in solution. It's not in its ion form. Which one's that? The NiOH2, that's the precipitate, right? I don't have to worry about taking that into account because that's a solid. Since it's a solid, it's not contributing any ions. So now what I'm worried about are how many ions is my excess reactant contributing and how many ions is my product reactant or product ions contributing. The easiest place to get confused on this one is to forget that you have excess reactants. Okay, that's why I like the ice table, because it makes it very obvious that I have excess reactant left and I have to think about it. So since we know both of those things were aqueous, we really just need to think about what they look like when they split into ions. So if I have 0.02 moles of NiSO4, that means I've got 0.02 moles of nickel ions and 0.02 moles of sulfate ions. Are we comfortable with that idea? Okay. Same idea for the K2SO4. If I've got 0.01 moles K2SO4, how many moles of potassium ions do I have? Careful. How many moles of potassium ions do I have? Why do I have 0.02? Yeah. Even though there's only 0.01 moles of this compound, you see how there are 2 potassium ions inside it? Because of that subscript? You want to be careful about that one there. So that's why that got doubled. But how many moles of SO4 ions do I have from K2SO4? Just the 0.01. Are we comfortable with those numbers? Okay. All I need to do at this point is list them out and do a calculation for concentration. So concentration, and have you seen that notation in the brackets before? concentration is just moles over liters. So I know that the concentration of the nickel ion is going to be equal to 0.02 moles over 0.300 liters. So 0.0667 molar. For the SO4, I want to be very careful here. How many moles of sulfate ions are floating around in solution? I've got 0.02 from the nickel sulfate, but I also have 0.01 from the potassium sulfate. So how many total moles of SO4 ions do I have? 0.03. And then the last one is just going to be K plus. Since that's only got one contribution, that is a fairly easy calculation. Oops, 0.1. So 0.0667 of the nickel and potassium, but 0.1 molar of the sulfate because I had two contributions of it. Questions? All right, again, this will all be available online, which would be a very good problem to work again on your own, and then watch the video, make sure you can get the same answer. I know we didn't cover redox stuff, but you still have some videos for that available online. If you have any questions while you're studying, feel free to send an email. Otherwise, good luck.